Welcome to a lesson with Dr. Powell. This is part 3 of a lesson entitled A Close Look at Continuity and Limits. Please look at parts 1 and 2 so you don't get lost on what we're doing because we're picking right up where we left off. In part 1 we talked about some definitions, preimage, codomain, image, and came up with the description of what it means to be continuous for a function on its domain. Pretty much a simple idea is the preimage of codomain fuzz is going to be fuzziness or fuzzy spots in the domain. Whatever that means, please look at part 1. All right, so part 2, we talked about what it meant to be continuous at just one point, looking symmetrically from both sides. Now, and with a delta epsilon type description. We're going to be trying to think of a epsilon delta description now for being left continuous. So continuous just on the left side on one side. So what we would like is that what we would like is that left half fuzz from A. Okay, so we're being left continuous at A, so left half fuzz, meaning we're not having a symmetric interval. We're not going to have something coming up on both sides of A, but just to the left of A over here. And we would like there to be, exist some fuzziness to the left side that'll completely map into a given codomain fuzz. So given a codomain fuzz, is there some left domain fuzz that'll map into it? Or come up into its images. So the images of every single point here and here will actually be images, will actually land inside of this codomain fuzz somewhere. That's the idea. To describe, to say that something is inside this left fuzz over here is to write this. In fact, I'll put this down right here like this. Okay, is to write something like this. All right, pretty much A minus x, requiring that it's positive, means that x is to the left of A. We're going to allow it to be equal to 0 so we can even include this endpoint right here. We're talking about left continuity up to a point. And we're going to assume that the function's equal we're going to assume that the function is defined at x equals A, that A is in the domain here. Okay, so that this description will work. All right, so so we have A minus x is going to be positive, of course, but we're also going to let it be less than delta. Why? Because we want this distance to be, well, we want it to be in here in this interval, A minus x, not to go further away from delta, away from A. Okay, so if this, right, if x is in the left domain fuzz from A, then all the points, well, the image of that particular x that we chose is going to be f of x. We want that image to not be more than epsilon away from the center of that codomain fuzz, which is f of A. So the distance between f of x minus f and f of A, we can write using absolute value, because it can be on either side of top and bottom. Here, we only want, notice there's no absolute value, because we only want x happening on one side of A, not on both sides. Here, we don't care about here. We just want the codomain fuzz to right here, it to just come up into there, right? So that it's getting close. So as we move just a little bit in the domain, that the y values are not getting far away. It doesn't matter where they're getting, up or down, but on the left, this is definition of what it means just on the left side, kind of as we're coming up to A on the left side. Okay, so, and we can write that this way. Given epsilon greater than 0, that refers to this epsilon codomain fuzz. So basically, given some codomain fuzz, there exists some left fuzz from A. That's what this means right here, delta greater than 0, such that if that, then the image point of f of x from that x that's in the left fuzz is going to come up here and be in that codomain fuzz. So let's look at an example of that, a piecewise function. So x squared on the left of 1 up to 1, and then 2 on the right. Okay, so so given some codomain fuzz and epsilon going up and down, all right, so f of a in this particular case is 1 and a is 1 as well. So we're plugging 1 in and getting that out right there. This is just an illustration of this definition that we came up for left continuity actually being a successful one for precision's sake, right? So I mean, the idea is we want precise definitions of things that where there's not going to be loopholes, where we're not just going to loosely say, oh, you just draw your pencil without picking it up or something like that. There can be some loopholes to that. I mean, like, we want some precise ideas here. Even talking about closeness, we got to be careful because of bizarre cases of things increasing with really steep slopes. So we got to be precise here as we move along. If in this particular case, so we have this codomain fuzz. Is there some left domain fuzz that'll put all the x values in that up into this codomain fuzz? Notice where I drew this dotted line right here. If I had drawn it further over here, think of taking x values out here. Their images are out of this codomain fuzz. So that would be too far away. So, but right here, that's as far as we can go to the left from 1, so that the x values, their images, will be inside this codomain fuzz right here, about 1. Okay, so using our description then, given the codomain fuzz, we want to find the delta. Notice I'm finding it. That's how I'm going to show it exists. Because in the definition here, I said there exists some left codomain fuzz by saying there exists some delta distance I could use for that left fuzz. But here, let's actually verify that by showing that, well, yeah, the delta exists. I mean, we can see in the picture, yeah, just draw it there. But seeing in the picture is equivalent to doing the algebra here. Like, writing this down is equivalent to seeing what's in the picture. And we're going to practice writing it out algebraically. So at this point right here, we just need to figure out what that delta is that pushes out over to there. And that's how we're going to verify this. So to do that, what we can do is we can think, all right, this y value right here, like epsilon down from 1, can be described in 2 ways. As 1 minus epsilon, right, epsilon down, or it can be described as the output of plugging 1 minus delta, which is the x value right here. So 1, we went delta over that way, so it's 1 minus delta. So plugging in 1 minus delta into the function f. 1 minus delta is less than 1, so we can plug it in to this part of the piecewise function. We square it, and so that is a description of the y value, and this is also a description of the y value. Set them equal to each other, and let's solve for delta. Notice when we take a square root, plus or minus, but we're going to only take the plus. Why? That's because, in particular, 1 minus delta, assuming delta is small, is going to be positive, because 1 is positive, right? So it's positive square root, and we keep going, delta is equal to that. 1 minus a square root of quantity, 1 minus epsilon. So that's our delta description. So we just verified there's a good delta that works, right? So there exists one. Oh, so we're illustrating the definition's working, right? For a given epsilon, there's going to be a delta. Show that there is going to be a delta. At least we did in the picture. And then we said exactly what it was from the picture. So the two together, at least for us right now, is going to satisfy kind of a good description of that, at least an intuitive one. So then we say, okay, what does this mean? This means that the x value is in the left fuzz that we chose, right? 1 minus x is going to be less than delta, greater than or equal to 0. There, okay, so if x is in that left fuzz, then yes, because I can see it in the picture by the choice of delta. Great. Okay, so right continuity, similar idea. We can kind of use the exact same idea, but in this particular case, we're going to have x minus a. X is going to be on the right of a point A, and describe that we can say x minus a is going to be positive and less than a distance delta. Notice I have or equal to 0, and that's because I'm going to allow x to actually be a. We're talking about continuity here. and we'll talk. And with limits, we actually omit that or equal sign. But for continuity, it's okay to keep it there. If we make an assumption that x equals a is, well, it can't even be continuous unless a is in the domain itself. So we can even be thinking about this at all, and so that's perfectly fine. Then we have that f of x minus f of a is less than epsilon, so we're in the fuzziness. So just on the right side. So it's the same thing we're just talking about, but just on the right side, right there. And stay tuned, because the next part will now address limits. Okay, we're going to talk about limits in terms of this this epsilon delta type description of continuity that we've been referring to. So that'll be in part 4 of this lesson. Thanks for watching.